So, um, chapter 7. We'll get there. I'm slow. So, why do we study AC circuits? Well, because part of it is because most of the power that we use today is done with AC power, and if you really want to know, the majority of why we do what we're doing is so that you understand in a plant or in a factory how power is used and how to control it. And when they say to you, we want to get a better power factor, we are going to do certain things to get a better power factor that you can actually understand what they're talking about. And basically, that's it. You may or may not think that we've done anything worthwhile up till now, but there are some very practical reasons why we study AC circuits, and then we get into this part where we talk about power. Okay, now I want to go back and I want to go into the course just a little bit and talk about some of the things that are coming up. Okay, so this is a project that we're going to do pretty soon, and you probably wonder, why do we jump from AC circuits into something like this? Well, because most of the circuits in a factory are that's a blank page. Come on, Ted. Most of the circuits in a factory are of how you want to say it, motors. So motors in general are what we call squirrel cage induction motors. They're induction motors. Which are nothing more than a big old fat inductor. So when you're looking at something like how many motors do you have in your plant, you're going to be asking the question, how do you control them, and how do you compensate for the fact that they're inductors? Okay. You see, I don't really have to compensate for the fact that they're inductors. Well, chapter 7 talks about that you do. And chapter 7 and I think chapter 9, chapter 7 is single phase power. I think chapter 9 is three phase power. But the only difference between these two is the square root of 3. Everything else is the same. So you talk about one, then you talk about the other, and we're talking about the exact same thing. It's just the fact that with the three phase, you are including the square root of 3 because you have three of them. Okay. So here under conduit project, someplace I actually have NEC. So this is what I was looking for. So I have all this stuff that goes along with that assignment, and these are just excerpts from the National Electric Code. So if you look at the National Electric Code and you start going down through it, you have all these things. And what are they? Well, they're single phase, three phase, the ampacity, the amps of each motor, horsepower of each motor. So you have a certain horsepower motor. What are the amps of that motor? And from that, you can find a wire size. And from that, you can find a diameter of the wire. And from that, you can do conduit fills. So you can determine how many wires and how full you can fill conduits, bringing them back from various locations back to a centralized location where you're going to have a motor control center, what they call an MCC. So on one side you have your MCC, on the other side you have all these motors. And how do you describe how you would control these motors through this motor control center? You have to have a wiring diagram that shows how you connect this to this. So in order to do that, you have to do this. Okay. And you say, well, you're going to tell me what kind of insulation to use. I'm not going to tell you what kind of insulation to use. You're going to find that there are a lot of types of insulation that you can use, and you have to pick one. Which is the best? I don't know. You decide. Owens Corning picked XHHW because it was a type of wiring insulation. Now you're talking about wiring insulation in a controls course, yes, or in a electrical course, because wiring insulation is something that is important because the different types of wire have different types of insulation. But XHHW wire, if you had a fire, the insulation around the wire, here's the wire and here's the insulation around it, would not necessarily melt off. It would just kind of cook in place, and you might be able to use it even after a fire. So there's a fire in your conduit, but you can still use the wires after the conduit has had a fire in it. Okay? Because the insulation does not necessarily, in that type of insulation, melt. Some do. They just melt away, and others don't. And this is one that just kind of cooks in place. So you can decide which one kind of use. Now, I'll tell you something about XHHW insulation. It's not the kindest insulation to strip. Electricians hate it. Other kind of insulation, they have these wire strippers and it comes right off. XHHW, you really have to work at it to get it off. Okay, so at the end of a wire, you have to strip away the insulation far enough so that you can actually attach the wire to a wiring terminal. That makes sense? So all of a sudden you're saying, well, you're putting electricians at a disadvantage. Yeah, we are. So again, that would be your response, or maybe you want to pick some other type of wire. THHN, MTW, there's all different types of wiring insulation. Machine tool wiring is MTW, machine tool wiring. But you can decide and then sort this all out and put this all together. And congratulations, at the end of that time, you will have built a wiring diagram, or some people call it a riser diagram. So it's a wiring fill diagram. Some people use it as, but anyway, if you show a picture of the different conduits with the different fills and the different sizes of it, and all of a sudden you start using Excel spreadsheets because they're the best way to add all these up and get them all finished off and all that kind of stuff. So that's that. Okay. So now we're talking about practical stuff. So if you know how to do a wiring diagram or a conduit fill diagram, it's one of the things that you can go as a freshman, sophomore in college and go to a consulting firm and said, our professor made us do this. I don't know why, but he made us do this. And all of a sudden they can say, okay, we'll hire you part-time because that's a skill that we need. In other words, we need people to be able to do that. And you say, huh? AutoCAD, you take AutoCAD and this, and then all of a sudden you can do wiring diagrams. Yeah, you can. So what you're doing is you're describing how an electrician wires a factory, is what you're talking about. So these combinations of conduit fill, rules for conduit fill, and all that kind of stuff. And what's left? Well, on your motor control center side, there is this thing called so you've got your motor control center sitting there, and they have things called buckets. So each one of these is one motor starter. It goes out and controls one motor, okay? So this is a motor starter. It's a bucket. Now, each of these motors has a size to them, okay? So if you have a 30 horsepower motor that you want to start, you have a 50 horsepower motor that you want to start, you have a 10 horsepower motor you want to start, okay? Now, if the person that sizes the project sizes it correctly, that motor will run at full load, okay? If they oversize it, if they undersize it, it won't start. I mean, it won't turn. Everybody understands that if you undersize a motor that and you want to turn, and the force that's necessary to turn that is more. If you're trying to lift 50 pounds and you have a motor that won't lift 50 pounds, what will it do? It'll just stall out. Everybody's got that in their head. It'll just stall. Okay. Now you can go the other way. You can say, I've got a 50 horsepower motor, but I'm only using a 10 horsepower load. What happens? It's running inefficiently. Okay. Motors run most efficiently when they're at full load. If they're not at full load, they don't run efficiently. So all that said, you want to get as close to 50 horsepower as you can if you're running a 50 horsepower load. Or in other words, you want to be able to do that. But loads vary. Sometimes you have something on the conveyor, sometimes you don't. Sometimes there's a heavier load on the conveyor than at other times. So you have to size the mechanical engineer, or you, if you're interested in doing that, if you size the motor correctly, you size it for the worst case. But at times, it's not going to run at that. It's going to run at less than that. So in that situation, it's going to run inefficiently. And what actually happens is, here's your vector for power, and here's your vector for V times I. Okay? Now, what is this? This is induction. That's the inductive load. In other words, that's your inefficiency. Right there it is. There it is. So as you get more inefficient, this works like this. It goes higher. All right? So it's up to you or somebody to make sure that this is running fairly efficiently. And you say, this is still not what I want. What I want is something that runs like this, and there is no inductive load. So how do you cure that? You add capacitors. Okay? How do you do that? Usually one capacitor per motor over a certain horsepower range. Now at Owens Corning it was 7.5 horsepower. Anything above a 7.5 horsepower, we put capacitors on. Now I'm sure today that it's less than 7.5 horsepower. That dates me because that was 40 years ago. Okay. But They still do. You still put capacitors on motors. So this explains what we've been doing, explains the fact that you will be asked to not only design the starter and the circuit that starts this motor, but you'll be asked to also add capacitors to these motors to be able to bring this power factor down to almost zero. Could be 10%, but if it's over 10%, then you're starting to lose efficiency. But you say, the load varies. Yes, it does. So basically, this is an average of all of them. You try to fit it as best you can based on the load in your factory. So you do a power factor, you do a study, and then you might add capacitors, you might not. Okay, what else can be done here? Well, it's not cheap, but you can add inverters, which are electronic devices that basically do this electronically. You don't need a capacitor with an inverter because it will reduce the voltage to reduce the current to the point where you're basically at this point already. So you don't need, with an inverter, you don't need a capacitor. You shouldn't have to use a capacitor. All right? So anyway, now, this is the current that you run without the capacitor. This is the current that you would run with a capacitor. This is less current than that. So do you size the wire from the motor starter to the capacitor based on this wire size or on this wire size? You size it based on this wire size. Why? Because these have fuses in them. And if the fuse blows, you go back to this until you fix it. Everybody follow that? So if you are sizing based on this current, and the fuse blows, all of a sudden you go to this current, and if the current is too big for that wire size, what will happen? You'll have a fire. So all of this stuff has to be if you understand what we've done up till this point, this makes perfect sense. If you don't understand what we've done up to this point, this is like, huh? You just do this because you're supposed to do this. Yeah, but now you have an understanding as to why you're supposed to do this. All right? So chapter 7 kind of ties it together, and then chapter 9 piles it on even more because that's three-phase, but the single-phase, three-phase issue is, it's the same thing. It's just you add the square root of 3. 3 numbers you need to remember in electrical work. Square root of 2, square root of 3, and 746. Those are the 3 numbers, and that's all you need to remember. Everything else you can usually look up in a book or something else. Why square root of 2? That's the difference between RMS and peak value. Okay? What's the square root of 3? That's the difference between single phase and three-phase. What's 746? Many motors do not rate in horsepower. They rate in watts. Okay? So how do you convert between watts and horsepower? Take the watts, divide by 746. Really 745.7, but who cares? It's 746. It gives me horsepower. So you get a European motor, it'll always be in watts or kilowatts, kW, thousands of watts. Then you divide by 746, and that gives you your horsepower. The only 3 numbers you need to remember. Everything else is just, you don't need to remember a whole bunch of numbers in your head as you're walking around, and that's why I like electrical, because I don't have to remember a bunch of stuff. I can just look it up or do it on the spot. But that's all you have to kind of in the back of your mind keep track of. Okay? So this is coming up. It's not yet, but we're going to assign this here in a week or so. This is what chapter 7 and chapter 9 is about. And this is why we've been doing what we've been doing up till now. Other than the fact that also in chapter 8, I think it is, we talk about resonance. And resonance is where you have your electronic circuitry where you cancel these two out and you just have the resistive circuit. And if you have a short resistive circuit, you can basically have very low impedance. And basically you can plot at that frequency, and this is a frequency plot. Now this would be frequency. You can go up and pick a frequency off and then come back down. Now why is this useful? Because what are radios built on? The ability to pick one frequency at the expense of all others. Okay? Running through this room, believe it or not, are all kinds of frequencies of waveforms. There are all kinds of. I mean, there's channel blah 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 and channel blah 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 and channel blah 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 and channel blah blah blah. And you can pick them all up, but you only want to pick up one, the one that you want. The one that you want to pick up is the one that you tune to, which is that one right there. All the other ones go away. So basically, if you minimize this and minimize these, you get that. You don't have to understand a lot to understand that you can pick off one frequency at the expense of all others. If you minimize the X sub L, the X sub C, and the R, you get a high peak. And that's the intermediate step of most radios does that somewhere or another. Now you say, well, it's all digital today. It's all digital. Kind of. I don't know. I don't get into the study of radio circuitry. I just, that does not get me going. But on the other hand, that's the basic underlying principle of how we pick off one frequency versus all the others, at the expense of all others. You use the idea of cancellation of the X sub L and the X sub C, and you minimize the R, and you pick it off. It's called a high Q or a quality factor circuit. High Q circuits are circuits that can pick off one frequency at the expense of all the others and gives you a high peak. So anyway, you're going to have fun, and then we're going to give you this other project that really takes some time, and we're getting them built right now. But it's a digital project, and it has nothing to do with this course, except for the fact that it gets into controls. And I'm going to wait to describe it, even though it's kind of fun. But this is what I want you to be able to do, and you can make good money as a draftsman or as a designer. But I don't want you to stay there. I want you to get through that phase. By the way, do you need to, as an electrical engineer, to be able to put together drawings that does this kind of thing? Do you think that's something that you might have to do? Or maybe you don't create the drawings, but have to review the drawings to make sure that they're right? Yes. Okay? You will. Why? Because you're dealing in a bid process. Okay? There have to be drawings made to bid to contractors. Contractors are not just going to come in and say, I'll do whatever you say. How many think that a contractor is just going to say, whatever you tell me to do, I'll just do for a fixed rate? No. What do? They bid the drawings. And if the drawings are not correct, what do? They ask for extras. And how much do you think extras cost in comparison to the original bid? Lots of money. So instead of paying at a certain rate, you're paying at a higher rate. It's a game. But you have to make drawings that are accurate and that show what you mean in order to get a correct bid. Once you've got the bid, the electrician comes in, puts it in, signs off that they've done their job, then it's your job to start the system up. Okay? Now, some of you are going to look at this and you're going to say, but boy, those electricians make a lot of money. Some of them do. Somebody was telling me that they went into a data center where there's a bunch of, oh, it was the guy on Mike Rowe on TV. He was on TV. He went into a data center, and there were 3 electricians working in that data center, and they were all pulling down $250,000 a year. They knew what they were doing, and they're very good, okay? Now, you can say, that's what I want to do. It's very repetitive work, and at age 50, 55, their knees go bad. Not everybody's, but a lot of them, because they're on their knees all the time. They just basically are on their knees wiring stuff in, and that's what they do. But on the other hand, it can be very gratifying work or not. I'm not saying don't do that. I'm just saying that in your life, you might find more challenge being an engineer designing this stuff as opposed to being there doing this repetitively. But I'm not telling you don't do that. I'm not telling you that that's not a good job. I'm just telling you that what you're being trained to do is to direct people like those folk to do what they're going to do. That's what your job will be, is to direct them. Okay? So you don't have to be the person sitting there tightening all the wires. You may end up tightening some wires in your life. I did. I still do. But, okay, enough. I'm rambling. But I want you to get a feel for where this course has taken, where it has taken you already, and then where it's taking you, because it does take you down this path of being able to do conduit fills and that type of thing. And there's plenty of work in the electrical field doing nothing but conduit drawings and circuit layout drawings. That's something that some people they'll sit there and do that all day. But I think you probably want to do something more. But on the other hand, that's up to you. Any questions anybody's got on any of this stuff? I'm rambling, but I want you to understand a little bit about where this is going. So anyway. So basically, power is equal to V times I, right? So in the study of power, so this is chapter 7, you have power is equal to V times I. And if you can't remember V times I, think of this professor doing this to you, okay? And if you can't remember V times I is equal to power, just remember the stupid professor doing this, and now all of a sudden you got this V times I in your head, okay? V times I. Okay, so that's that. Now, what V and what I? These are RMS values. They're not peak values, okay? And if you want to know how you can prove that power is equal to that in a resistive load, you can actually show that, okay? Now, if you have a phase shift, this is for DC, okay? Now, in a phase shift environment, you have an AC, you have current, you have voltage, and you have current, but there's a phase shift, right? Everybody agree with that? The power you get out is V times I times cosine of the angle theta in between the two. What you put into it is V times I. This is the watts. This is what we call reactive power, or we just call it V times I. If you ask me what this is, it's V times I, okay? It's sometimes referred to as S. This is P, this is S, and this is VARs. This is V times I times sine theta. This is what you put in, and you don't get a dime back of anything back from this. You do not get zero. You get zero out. But this is what you have to put in order to get this thing to work. To get the motor to turn, you've got to put this in, you get nothing back. This is what you measure These are called VARs. This is the foo-foo dust. Okay? But it's real in the sense that you have to put it in order to get your motor to turn. But you don't get anything back from it. Okay? This is what you get out. This is what you get out. Okay, this is mechanical power at the spinning of the rotor. Now you say, but motors are not 100% efficient. No, they're not. So then you devalue this to get the actual, what it turns to turn the shaft in the conveyor, because you might have a reducing gear, you might have other gears, you might have other things, and each one of those takes some power away from this. This is the starting point for what you get out. Everybody understand that? There is an inefficiency by the time you take this. You have to devalue this in order to get something turning on a conveyor, okay? To get a shaft turning on a conveyor, you have to do this times 0.8 or 0.7 or 0.9 or whatever. You don't get 100% of that out. So does that make sense? So up front, you have to spend this to get magnetic energy to turn the motor. This is what you put in, this is what you get out, and then you have to start devaluing that based on the mechanical system. So you're getting 80%, 90% of something that you've already devalued by this because of this stupid angle? And the answer is yes. That's why we use capacitors, to bring this number back down. Okay? So that's the whole idea of the power triangle. When people talk to you about the power triangle, they're talking about this, right here, on this. And then they devalue this based on real world. Okay, so does that make sense a little bit? They call this the Q factor. This is the Q. They call this the S, the Q, and the P. All right? These are watts. These are VARs. The units of this is watts. The units of this is VARs. The units of this is V times I. Or this is V times I. Okay, so any question about that? The power factor is the cosine of theta. So when they talk about the power factor, they're talking about the cosine of theta, the angle. You have a power factor of 0.8. What does that mean? Crank up our cosine of our cosine of 0.8 equals an angle, and that's the angle of this guy. That's all you got to do. That's all you got to remember in this chapter, all right? And you're done. A couple of you just came in. I've got a couple of extra labs up here that you can pick up. And the other stuff is over there, which is the stuff that was graded before Tuesday. I haven't graded anything since Tuesday, so that's where we're at. We're going to do lab 7 today. I don't know if we're going to do another lab or not. We probably will do lab 8, but I haven't looked past lab 7, honestly. We never got past lab 6 in prior years. You say, well, why don't you just stop now and we don't have to do it? You should do lab 7. And when you get started on your project, that's going to be 4 labs worth. It's going to take quite a while to get that done. But I want you to be able to understand that side of the equation of what you're doing in your career. What part of it is this part, and what part of it is that part, the controls part. There's more to the controls part than there is to this part, but they both are necessary in order to be a controls engineer. You have to walk out and say, those conduits are being done correctly, or something like that. You have to be able to say that. Now, some of you don't necessarily want to go out into the factory and work in that environment, and some of you can't wait to do that. And I understand that. Some of you are going to say, I would rather program a programmable controller or do something else than go out and do that. And that's okay. Some of you are going to love climbing ladders and checking other people's wiring, and that's going to be your life, and you're going to say, that's excellent. That's an excellent way to spend my life. That's okay. Electricians aren't necessarily your friend. They're not your enemy, but they can also be very detrimental. I was in a project once where I was kind of one of the odd ducks because I'm a professor, right? I'm not supposed to know how to do all this other stuff. Well, guess what? For 15 years, that's what I did. So from 1971 to 1986, all I did was control engineering, and that's what I'm trying to get you to do, or teaching you what to do and where to look. And after 1986, I started being a teacher, but I didn't stop being a controls engineer because I kept for 15 more years, kept going out and working and doing stuff that was consulting work for the most part, doing the same thing. In '01, I worked on a project that was working with a company that basically was a beef producing plant. And I wrote the programs to collect the information from, it's a slaughterhouse. It's a huge, huge, huge slaughter facility for cattle in Arkansas City, Kansas. And I wrote the programs to take the information as the processing was being done and take that information and take it to the higher level computer system to collect the information on how they got paid, how the ranchers got paid, how many pounds that cow was, and who owned that cow, and all that kind of stuff that went up. So anyway, my point is this. I was working, we were part of a subcontract group, and there was another part of a subcontract group, and they were the actual electricians doing most of the work. And I would walk up to them, and they were doing things that were totally against any kind of, how do you want to say, the right way of doing things. And I didn't scream and yell at them, but boy, I knew when things were being done that shouldn't be done. And the example that I had was, I mean, I couldn't believe that they were doing this. But so you have a control panel over here, and you have a bunch of devices over here or wherever, and in between them you have conduit, or you have, and there are pull boxes usually in the middle someplace. They have to get the things to work. There's pull boxes, okay? Now the rule in most people's mind is you do not go into a pull box and junction and start building circuitry out of a pull box, because one end of that wire is here, the other end of that wire is here, and you don't take a wire in here and cut it and then do something else with it and then do something else. You don't do that, okay? And they were constantly. Well, we need some 110. We'll go in and take a little circuit with 110 and we'll go do something with it over here. Why is that not proper? Because the original drawings did not show anything like this. So you're all of a sudden, you're the third person in, and you're the person that's looking at the drawings that showed from here to here in the control circuit from here to here. But also there's something going on over here. You have no clue what's going on. What do you do in a situation like that? Third person in has no clue what went on. Does everybody understand that? You're totally blind. You have no clue as to what they did or how they did it or what is going on. You have no clue. Anyway, we did okay. I got paid. The basic thing most times a consultant can say is if you got paid, you were good. You may not finish the project, but you at least got paid. And I got paid. And most of the things that I did worked. Nothing happened bad on my watch. I did a lot of stuff that was very interesting. One other one, and I'll stop, but we had, this is the kind of stuff you get into. They're going to switch their inventory system, okay? They're going to switch their business part of this over to another system. And the group that was doing the inventory control had the software package that they were going to put in, and they were going to do all that kind of stuff. So basically, we had a barcode on the box. And here's the box of beef. Okay? So there's a box, has a bunch of packages of beef in it, wrapped with paper, wax paper around it. So we have to take this barcode over a scale, take that barcode, print a new barcode on a sticker that has that barcode plus the weight. Okay? Sounds easy. Not. So this scale was handed to us on a Friday. And it said, Monday morning at 8 o'clock, we're going to be wanting you to do this. The other guy that was with me, now, and the guy that had written the code that read this and did this left for the weekend. Okay? So we had the program supposedly working, but we didn't have a clue. And then we had the scale, we had this part of it done. And I commented to the guy, I said, we will have probably 4 or 5 major gotcha problems that we'll have to solve before Monday morning. And he looked at me and he said, you're probably right. We worked every minute from Friday afternoon to Monday morning. We slept, but basically 14-hour days trying this stuff out Saturday and Sunday. Monday morning at 6 o'clock, here they came. Boxes came down. We discovered that we needed 4 seconds between boxes in order to be able to get this to work. They were coming at a faster rate than that. What does this professor do? You ever see the Lucy program, Lucy and Desi Arnaz, where the pies are starting to come down the conveyor belt, and they're taking these pies? And did you ever see that? That's an old thing with Lucy and Desi. And you ever see that? Most of you never seen that. Here's a conveyor belt coming down with pies, and they're coming down at a fast rate, and then they come down at a faster rate, and at a faster rate, and a faster rate. And these 2 women are trying to put these pies someplace, and they don't have enough places to put them, and they finally start throwing the pies at each other. This woman that's supposedly manning this position, and I, ended up with these boxes. You had to put the boxes up someplace, 70-pound boxes, cardboard boxes. You had to put them someplace and then run them through again when there was a gap. It had to take more than 4 seconds. We got it down at the end of the day to 2 seconds, which is fast enough to take them through. And it worked. If we hadn't done what we did all weekend long, we would have never been able to work it all at all. But the 4-second gap to the 2-second gap was we worked on that morning, and we finished up getting it down to 2 seconds, and we actually got it. It would work. Everything would take through it. By noon that day, everything was going through. But in the process, there were boxes everywhere. I mean, literally in that room, there were boxes on boxes on boxes on boxes on boxes all the way to the ceiling in that room. Again, that's what I did as a professor. So it was interesting. That's control engineering is what it boils down to. You never know. You never know what you're going to get into. Okay, so this is what we're talking about. Power, apparent power, which is this is the arrow. This is what you're really putting in. Volts times amps, apparent power, and reactive power. So this is what you get out. This is the V times I, and this is the foo-foo dust, the stuff that you put in but you don't get anything out of. Okay. So we have some problems with this, and I think I assigned 7, 8, and 29. I'm not really sure. And by the way, if you have looked at the syllabus, what? It gets kind of sketchy after this point, doesn't it? It doesn't say that you're supposed to do Lab 7. We're going to do Lab 7. I got to rework the syllabus, and I will, hopefully over the weekend or sometime in the near future, rework the syllabus to update what we're actually doing in this chapter. But this chapter is pretty straightforward. If you understand the idea of that simple triangle, you've got it. You basically don't need a lot more. You don't need to understand all this other stuff. Just understand that triangle. It's called the power triangle, and it is pivotal to being able to understand how power works in a factory and why we put capacitors on all that kind of. Why we do all this stuff? Why do we do it? Because the power triangle, right there it is. Okay? You'll get this again and again and again and again and again. The only difference between this chapter and the three-phase chapter is what? These have the square root of 3. This is this times the square root of 3. This is this times the square root of 3. This is this times the square root of 3, and you're done. It's the same thing, except for the fact that you got 3 wires instead of 2 wires. And again, this is all having to do with that angle. That's all it is. There's a very bad power factor right there. What are you doing here? Well, we're getting this little bit out, but we spend a lot of foo-foo dust. And we have to put this much in. Not a good project, is it? This is not, you would say this would not, I'm having to spend 80 cents to get out 20 cents. That's not a good return on your dollar. Okay? And people don't like it when this kind of stuff happens. Can this happen? Not this bad. Fortunately, this is not in a factory situation, but you can see this occasionally. By the way, an aside. What is this a picture of? What is that? It's a transformer. Okay? It's easy. What's this? It's an auto transformer. Commonly known as a variac. Those things exist. Oh, yes, they do. Now, what are the rules? Turns ratio, 3:1, same rules. They work the same, okay? Now I'm going to ask you, current, let's say is 100 milliamps going in. Turns ratio is out. What's going out over here? 300 milliamps. Where did the 300 milliamps come from? Yes, sir. I know, but I only have 100 going in, and I've got 300 coming out. How did that happen? It's like I'm conning you. Like, I'll give $1 to whoever can tell me how you can explain that. Because where did it come from? Where did 300 come out of 100? You see, it can't. I put $100 in the bank and I get $300 back. Let's really get weird. Let's put it 100 to 1. So I put 100 amps in and I should get a whatever out. Can't do that, right? Yes, you can. Yes, you can. How? AJ, how can you do that? How can you explain this circuit right here? You can today explain it. You have the tools to explain it. You have all that you need to be able to explain this today. I forget your name. Huh?
I don't know.
Everybody see the question? Where did the 200 milliamps come from? Ashley? Does everybody follow the question? Evan, what? No, it's not resistance. How do you explain this? This is actual real. You can actually make this happen. Yes, sir. I'm going to explain this to you, and this may look real weird, but this is how the vectors go for this, okay? Here's my incoming power. Here's my one, and here's my other one. These can be as long as you want. These can go really high. This can be little, big, and big. So you can have this really big, but it goes like this. It goes at a high angle. You say, huh? That's all it is. These vectors, the vector going here and the vector going here, can be very different from the... Anyway, so the vector going here, one goes this way, one goes this way. These can be very different, but that's what can happen. This is what's coming in, this is what's going out, but this can be very different. This can be very high. Yes, it can happen, and that's how you explain it with vectors. Now you believe that vectors actually do have a place because you can actually do this in the real world. And how do you explain it? Right here. It's not foo-foo dust. It's reality, but in essence what you're trying to say is all this stuff can be done. It just, when do you do it? You very rarely do it, but you can. Okay? Any questions about any of this stuff? Because we're going to get to the problem. We're going to go back to working problems. I promise you, we're just going to go back to doing the regular stuff. But I want you to get a feel that this is real. This is not just all theory. And I think that's probably what I'm trying to convey to you, even though I'm not maybe doing a very good job. Anyway, it's real. This explains why you can do this. It's vectors. And this part over here can happen. You don't want it to sometimes, but it can. And you say, well, I'm just going to do this. I'm going to buy an inverter. Every place where I see, I'm going to buy an inverter. What's wrong with that solution? They cost a lot of money. So your price of entry for inverters is the upfront cost of buying an inverter. But once you buy them, a lot of these problems go away. Power factor goes away, all that other stuff goes away. Inverters are nice. You can start motors with them. You can control the speed of them. You can do all kinds of stuff with motors with an inverter. A good inverter is your best friend. But the upfront cost of buying an inverter is what? They're not cheap. $5,000 or $10,000. I don't know exactly what the price of an inverter for a 5 horsepower, 10 horsepower motor is, but it ain't cheap. And it takes time to set it up. We're going to set up a motor and we're going to set up inverters in 4350, and you'll get a chance to see how a motor works with an inverter. But inverters can control that. They can do all this stuff, and they make all this stuff go away because they do all that stuff for you. But it's not cheap. Okay. And again, I don't want to belabor that. But they're your best friend. If somebody says we're going to have to put an inverter there, you smile because they've decided they're going to spend the money on them. And you can do anything you want to with them. Okay? So again, this is just a chapter that we can go through, and we are going to go through a couple of problems. And basically, but if you understand the basic idea of a power triangle, you're in. Now, this is the efficiency of the output over the input. Now, this has to do with what? This efficiency has to do with once you get this is your raw, this is your watts. Now, that's coming out of the motor. That's just the motor itself, not any gearing or any the physical gearing of the motor, not the gearing of the motor, but the physical shafts or the bearings of the motor. It takes some of this efficiency away. It takes away from this. So the efficiency is the output power over the input power. So the input power is this. That's your 100% power. So the efficiency is the output over the input, or they call it nu. That's the Greek letter nu. If anybody asks you what's nu, you can say, well, it's output power over input power. So if you want to be a smart person, you can say that, or you can, anyway, what's new? So that's that. So that's this part right here, okay? So here is a thing with that, and you have, okay, the output is 1.2 horsepower, which is equivalent to, in watts, 895 watts, and then I have an efficiency of something, and you have to then say, okay, so I have so I have to put in so much to get, now he goes the other way. He goes, this is, my input is this. So it's divide, okay, you divide by new, and then, okay, so this is where I say, I need 1.2 horsepower. Okay, I need 1.2 horsepower, but my efficiency is 0.9. So what must I put in? What must I put into this arrow in order to get 1.2 horsepower out? I have to put in 994 watts instead of 895. I have to put in 994. So that's how he does that. Again, different people design this differently, but that's how he does it. So we have to follow his rules in this course for this book. But anyway, this is the pure out of the motor watts. Then you degrade that to get. He's saying you need a 1.2 horsepower. I'm saying the 1.2 horsepower is this, but he's saying the 1.2 horsepower is this at the shaft. In other words, you have to degrade it a little bit, so you have to do this degrading part of it. So that's okay. We can live with that. It's always who defines it in order to figure it out. Okay, now that's basically it. Now we get down to this stuff and we say, okay, now here we have some loads. Some of them are purely resistive loads. Some of them are what? Reactive loads. And then we have to do something with those reactive loads. So basically we're building we're building a triangle a piece at a time. So if you understand, we're doing some of this, and some of this, and some of some of this. So you add them all together, and you get this plus this plus this plus this plus this. You actually get the total, and then you get your final answer. So basically, this stacks on top of that. That makes sense. So if he talks about a purely resistive load, this is a purely resistive load. If he talks about a reactive load, this is a reactive load, and this is another reactive load. And these reactive loads stack on top of each other until you get your final answer. So that's what he's doing here. Okay? And he's also doing this efficiency thing, which is basically new, which is this thing right here. So he's doing that. And now he's finding the total based on all of those. Okay. So here they are. Here's your total district, your one, and here's your second one, and your whatever. And that's total. And now if you had a capacitive load, if you had some capacitors, there they are. And they're your final answer. So he's adding capacitance to the reactance to bring this down to something that's a little bit nicer. As long as you get close, you don't have to. What's the sign of this angle? 0.999 or 0.990 or 0.980 or whatever. You're within 100. You're within a percent or two. And if you understand the idea of loading will put you back and forth. You might be a little bit up, then you might be a little bit down. But you just take an average of it, and you say if you're. Rule of thumb is if you're 0.90 or higher or better, you ignore this. So if you're 90% or better, usually you ignore. You're good enough. Anyway, so that's pretty much this whole thing. So let's go through and look at some of these problems, okay? Done talking, now we start doing our work, okay? So here we have a problem, right? 7-7. By the way, these problems are the same as what you've had before. There's nothing new other than new here. Sorry. The only thing new in chapter 7 is new. All right, 7.7. So here we've got it, 120 volts. We've got a capacitor. We've got a resistor. And we have an inductor. Okay. And this is a parallel circuit, right? So I for the resistor is 120 over 20, or 6.0 amps. Okay? I for the capacitor is 120 over minus J25, or 4.8 at angle 90. I of the inductor is equal to 120 over J40, or 3 at angle minus 90. Add those all together. How do you do this? The same way you did them before. 6.264 at angle 16.7. Okay? What is the power? V times I, total I. So it's 120 times 6.264 at angle 16.7. Draw the power triangle. Okay, what is it? V times I is this, right? 120 times 6.24 is what? Times cosine theta. What's this side here? It's V times I. This is equal to 751.68 at angle 16.7. That's equal to V times I. So this is the 751.68. That's that number, okay? What is this number? 719.97. That's your watts. That's this times cosine theta. This is that times sine theta. What is that? 216.0. Now this is in watts, this is in vars, and this is in V times I, the units. And you're done. What's the power factor? Is equal to cosine of theta is equal to what? 0.9578. And that's it. That's all you got to do. Questions? Is there anything here that you haven't done before? 10 times? No. You've done this. It's just now looking at it from the practical point of view of the power factor. Now, is anybody going to beat you up with this power factor? No. Anything above 0.90 is usually okay, it's acceptable. Some people say 0.95, and you're 0.957, so you're okay. But they're going to have a rule of thumb for your factory or for your plant or wherever you're at. They're going to say, what is our power factor and what do we need it to be? And they get a bill from Toledo Edison or whatever, and they give you a power factor, and they tell you what your power factor is. And sometimes there's a bunch of weird rules, too. They have a guy comes out and talks to you, and he comes out and explains your bill. This is your bill. This is how you have to deal with that. And there's a period where if you have a bad power factor, that you have that as a penalty and all that kind of stuff. They explain your bill to you. And you go through this and you say, now how can we beat this down? It's costing us a lot of money. We can't afford this. We got to get this better. So you do load shedding, you do whatever you have to do. Most of the time you don't do much because you still need the power in order to make the product that you're trying to make to sell to make money. So you don't do too much. But you are required, some of you will be required to look at the electric bill and try to figure out how to get the price down. So this is what they do right here. Number 8. 7, 8, and 29 are the three that I worked, and I think that's about all we're going to do in this chapter. So I'm going to work them for you. I'll put them in as the assignment, I think, and that's all we're going to have for this chapter to do as far as problems to hand in. But these are the kind of problems that I would hold you responsible for chapter 7. But they're not anything other than 29. They're not anything new. So basically, you're not being asked to do anything new. Okay, 7 to 8. Okay, so the circuit, determine the apparent power, the real power, the reactive power, and the power factor. The source is 120 volts, blah, 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 blah. Okay, so this is the same as the one above. Okay, so number 8, same thing. I'm going to let you work number 8. I'm going to go down and work number 29, which is different. It's asking a little bit different question than that other one. So basically 29 is, okay, this is the stacking of the various triangles to get one master triangle, to get one big triangle. So here basically you have 4 loads. Load 1 is 1.2 kilowatt resistive loading. So basically load 1 is load 1 is power factor looks like that. 1.2 kilowatts. Okay. Load 2 is 400 watts resistive. So load 2 is 400 watts resistive. When it says resistive, that means straight, no inductive or no capacitive load. No foo-foo dust, no J's in it. Okay, so there's 400 watts like that. Load 3 is a 0.5 horsepower motor that has an 80% efficiency with 0.7 lagging power factor. Okay, so now we've got to deal with all this other stuff. So load 3 is like this. It's got a it's got along the x-axis, it's got something, and along the y-axis, it's got something as well. And we just don't, we have to figure that out, okay? And then load 4 is another one. And this one is worse. It's 85. The one is 0.75 or 0.7, and the other one is 0.8. So you've got 2 of these that have an offset, okay? So now you have to add them all together and get a final answer, and that's the hard part, okay? So what's your voltage? 240 volts. So you got voltage is equal to 240. So V times I is this. So what is my amps here? What is the amps for this one? It's V. Oh, it's power divided by, okay, it's power divided by V, Ted. So the I here is equal to power divided by V, or 1.2 kilowatts divided by 240, or what? 5 amps. And it's at angle 0. Here, it's I is equal to 400 watts divided by 240, or what? 1.67 amps at angle 0. Now, what is the third one. It says a 80% with 0.7 lagging power factor. So 0.5 horsepower motor. So it's a 0.5 horsepower motor. So 0.5 horsepower is equal to how many watts? How many watts? It's, yes, 373. And you have an efficiency of 0.8, so it's 0.8. So you have a need here of how many watts? 466.25. So we have a need of 466.25. Now that's the real. So the angle theta is equal to the cosine minus 1 of 0.7. What is theta? 45.57 degrees. Now, this 466 is along this axis. This is 466.25. What's along the y-axis? You got an angle. Here's what you got. You got 466.25 along this axis. You've got, and you say, boy, if I now I know why I needed to study trigonometry, right? Whatever. Okay, so I got 466 along this axis. I've got an angle here of theta is equal to 45.57 degrees. What is along the so I divide 466 by I don't really need the power up here. I just need this is okay. This is 466. That's along the x-axis, and what is it along this axis? This would be 466 divided by what? What's along this axis right up here? What would this be? Divide that by what? 0.7, and that gives you this number right here. And then along this axis, it is that number times sine of theta. What would that be? I don't have that answer in front of me, but it's 66.25 divided by 0.7 is equal to 666. So this number here, this is V times I is equal to 666.07. That's 666.07 divided by point. Okay, 666.07 times sine of theta, sine of 45.57 degrees is equal to 475. So this is, right over here, this is 475.6. Now, this is my V times, this is 240. What's the amps in this direction right here? What are the amps? What is the I in this direction? The real. It's 466.07 2.75 divided by 240, which is equal to what? 2.77. So that's my real. And what is my Q, or what is the current here on this side? The amps here is what? 475.6 divided by 240, or 1.98. So here I have a current is equal to what? What is this current here equal to? 2.77 plus 1.98 J, or an angle of 90 degrees. So I have that one. Now my fourth one, I'll give it to you, is the real for this one is this fourth one is equal to 4.57 plus J 2.74. Now I add all these together. I add my reals is equal to 5 plus 1.67 plus 2.77, which is this one, plus 4.57, and that equals 13.18 amps total. And then my imaginary, I imaginary, is equal to 1.98 plus 2.74, or 4.72. And that's my imaginary I. That's what I have to put in order to get that to work. And that's my final. This is the real current, and this is the imaginary current, and there's my final angle theta of the whole thing. So in other words, I feed all this stuff. Some of them are decent, some of them are not decent, but there's my final answer, which is the real side is 13.18. My imaginary side is 4.72, and then I get my angle taking the tangent of those, and I'm done. Well, I didn't explain that very well. We'll probably go back over that a little bit more, but that's chapter 7. If you really want to get down through it, that's basically it. I should redo that again and explain it better. Well, we'll review 2029 again, and I will update your syllabus over the weekend and try to have that taken care of. So by Tuesday of next week, your assignment for chapter 7 will be on the syllabus, but it'll be those 3 problems. And we'll have some assignments down the road and clean it up a little bit. Any questions anybody's got? I'm going to shut down, and everything's pretty much, you go to lab, I'll see you in lab. I'm going to grade stuff while I'm in there, finish grading the stuff for you, and we'll get taken care of. Take care, and I'll see you.